We've talked about vector spaces, and we've seen many examples of vector spaces. We now want to talk about mappings between vector spaces. There is a special kind of mapping from a vector space V into another vector space W called a linear transformation. And a linear transformation is a function t from V to W that satisfies the two properties. One, t of u plus v is equal to t of u plus t of v. This is for all vectors u and v in V. Number two, t of c times u is equal to c times t of u for all vectors u in V and for all scalars c in R. Let's do an example. Consider t from R2 to R2 defined by t of V1, V2 equals this for the first component and this for the second component. Show that t is a linear transformation. Okay, so we have to show those two properties. The first one, t of u plus v. Okay, let's say u is u1, u2, and v is v1, v2. So then that's t of u1 plus v1, u2 plus v2. Okay, this is what we get when we add u and v. Now we just plug this into our definition of t. So the first part is negative the first component plus 3 times the second component and for this second component we get 4 times this minus 2 times this. Okay, so now let's distribute this negative sign. And so we get negative u1 minus v1 let's distribute the 3. So we get 3u2 and 3v2. Here let's do the same thing, just rearranging a little bit. That's 4u1 minus 2u2 from here, plus 4v1 minus 2v2. Okay. So then we get this. Let's look at this in terms of groups, like that. Okay, so we get this vector plus this vector. If we look at this part as a unit, and this part here, we get this. Okay, so I just broke it up, looking at it as the sum of these two vectors. Okay. But now notice that this part here, that's just t of u. And this part here, that's t of v. Okay, so the first condition for a linear transformation checks out. Let's check the second condition. We want to show t of cu is c times t of u. Okay, c of u, c times u is cu1, cu2. And then we apply t to that, so we get this vector. Okay, this is just from the definition of t. Now let's pull that c out from here and here. Same thing on this side, pull that c out. Okay, and finally from this entire vector, pull that c out. Okay, but notice that this part here is just t of u. Okay, so our second condition checks out. Let's do another example. Consider t from R2 to R2 defined by t of v1 v2 equals v1 plus v2 comma 3. show that t is not a linear transformation. Okay, well, let's check t of u plus v. That's t of this vector. Okay, now I'm just going to plug this into the function t. It says take the first and second components, add them together. The second component is just 3. Okay. So that's t of u plus v. Let's see what t of u plus t of v, let's see what we get for that. Okay, first applying it to u. And then applying it to v. Let's add. And I get this. But notice that here the second component is 6, but the second component for this is 3. So these two vectors can't be equal. Okay. So this is not equal to t of u plus t of v. Okay, so the first condition for a linear transformation is not satisfied. And we can stop here. We know that t is not a linear transformation because it has to satisfy those two properties. But let's just check anyways. T of cu. Let's see what happens. Okay, that's c of cu1, cu2. Apply t. And we get this. Let's see what c times t of u is. I get this. Let's distribute that c. Okay, notice that these two vectors, the first components are equal, but look at that second component. So 3 is not necessarily equal to 3c. At least they're not always equal. If c is some other number than 1, let's say c was 2. Okay, so it's not true that this is equal to c times t of u for every c. Okay, so the second condition for a linear transformation also fails.